Hello, good evening, and today we are having welcome to Column Cymru revision sessions. The session this evening will focus on AS Mechanics Equations of Motion and will be presented by Mr. Weatherhead from Porthcawl Comprehensive School. The session will last around 45 minutes, where Mr. Weatherhead will run through relevant content. If you have any questions during the session, please use the question and answer section and we'll do our best to answer. You will also see there's a hyperlink in the question and answer section. If you're happy to leave your name and email address, we would love to keep in touch with you so that we can send you information about future events. You can click on the link at any time during the session. Today's session will be recorded, and the recording and any relevant resources will be uploaded to e-sgol website under the Column Cymru tab. Thank you. Over to you, Mr. Weatherhead.
Thank you very much, Mr. Mackenzie. Okay, so we're going to cover a few different things today. We're going to start with the equations of motion and where they come from, which has been taken off this year's specification as an amendment, but is usually on there. So I'll leave it on in case you're watching this in the future next year. We're going to look at using the equations of motion and the standard SI units, and then we're going to have a look at some velocity time graphs as well. Okay, so if we go straight into it, we get our equations of motion all from a velocity time graph that looks like that. So this is a constant acceleration problem, and you can tell it's constant acceleration because the gradient is linear. Okay, and then SUVAT stands for displacement, initial velocity is u, final velocity v, acceleration and time. And the SI units for each of those, displacement would be in meters, initial velocity in meters per second, ms-1, final velocity in meters per second, acceleration in meters per second squared, because it's meters per second, and time in just seconds. So you'll see on some later questions where we are working in kilometers that there is some adjusting to do to get yourself into SI units. Okay, so the main two things you need to know about these graphs. If you want to find the acceleration is the rate of change of velocity, and that is the gradient of the graph. And displacement is the area underneath the graph. Okay, and there's a few ways we can do that. So if we look at, first of all, one method of finding the area under this graph, I put a line down there and we say that this graph is t seconds wide. Okay. And that's to use the trapezium formula. Now, the trapezium formula at GCSE is a half a plus bh. Our trapezium has been turned 90 degrees from what it would normally look like you would use for the trapezium rule questions at GCSE. So we've got a, b, and h is actually the width. Now, if we use the values we've got on our graph, so the area, which is the displacement s, is a half of u, which is the height on this left-hand side, plus v, which is the height on the right-hand side, times by the width, which is t. And that gives us one of our equations of motion. Okay, so s equals a half u plus v t. We're just finding the area under the graph. Another way of finding the area under the graph then is to split it up into a compound shape. And that compound shape would be made up of a rectangle on the bottom and a triangle on the top. The height of the triangle is v minus u. Okay, so if this was 20 and this was 12, the difference would be 8. So v minus u. The height of this rectangle is just u, and the width of both shapes is t. Okay, if we look at the gradient first, because that is actually going to help us to do the area. So the gradient is the change in height divided by the width. The gradient gives us our acceleration. So acceleration is v minus u, the height of our triangle, divided by the width, which is t. If you rearrange that, bring t up and multiply, you get at equals v minus u. And then if you bring the u to the other side, you end up with v equals u plus at. So there's another equation of motion there, v equals u plus at, so that's 2 so far. Okay, to get the next equation of motion, then we actually need to use this line of our workings, and we're going to substitute it in here. So instead of writing it as v minus u, we can write it as a t, and we've got a width of t as well. So the area of that triangle is a half the base times the height. So that's a half times t times at, which is a half at squared. Okay. Add that to the area underneath in the rectangle. Now it's just a rectangle, which is t wide and u tall, so that's got an area of ut, and you've got your next equation of motion. The total area under the graph is ut plus a half at squared. Okay, so that gives us 3 equations of motion. And what those 3 equations of motion all have in common so far is that they've all got t in them, which is a bit limiting because you won't always know the time, you won't always need to know the time. So it's useful to have a 4th equation of motion that doesn't have t in it. Okay, and to do that, I'm just going to go back to the first equation of motion that we found, and that was s equals half u plus v t, and then rearrange that to make t the subject. So 2s equals u plus v t, and then taking u plus v underneath, 2s over u plus v equals t. If we then substitute that into v equals u plus at, what we get is that v equals u plus 2as. Okay, so that's 2s times the a that's already there over u plus v. Okay, now I want to rearrange this slightly. So bring the u over, v minus u equals 2as over u plus v. If I move this down slightly, I don't want this fraction in my equation, so I'm going to bring u plus v up together, and that's going to multiply what's already there. So that's v minus u, and then u plus v equals 2as. And then if you expand out those brackets, you get v squared minus u squared equals 2as, and v squared equals u squared plus 2as. And that's our 4th equation of motion. But remember, the crucial difference with that 4th one is that it doesn't have t in it, but the other 3 do. So when you're selecting your equations of motion, you know, have a look at which one is most suitable. Okay, then I've got 3 different problems here, all using different equations because they've all got different initial values, initial conditions. And what I would strongly advise you to do, and I do this in my classroom as well, is before you do anything else, just make a note of what you already know in terms of S, U, V, A, and T. So in this first question, we've got a car accelerating from rest. Now, from rest means that at the beginning of this problem, it's not moving. So our initial velocity is 0. I'm not going to put the units in, but they are all going to be in the SI units I mentioned earlier on. We accelerate at a rate of 3 meters per second squared. So A is 3, and the time is for 15 seconds. It's worth noting, by the way, that you can't use any equation of motion unless you've got 3 different variables. Okay, so we've got U, A, and T in this example, so we're good to go. We've just got to pick the right one. We're trying to work out the final velocity, so we're trying to find V. That means we just need an equation that's got V, U, A, and T in it, and that would be, so picking from over on the left-hand side where I've got all 4, look, V equals U plus AT. So V equals 0 plus 3 lots of 15. 3 lots of 15 is 45, so V is 45 meters per second. Moving down, a lorry driver is initially travelling at 35 meters per second, so there's your initial velocity, so U is 35. When the driver sees a red light ahead, he decelerates at a rate of 7 meters per second squared. And you need to be careful with deceleration. It's slowing down, okay? That means we put it in as -7, okay? If you put it in as +7, the truck will speed up and never slow down, okay? And the question says, how far does he travel before stopping? And stopping means then that our final velocity in this question is going to be 0. We're going from 35 to 0, and the only way we can do that is with a negative acceleration or a deceleration. The question asks us how far does he travel? So that's displacement. We'll talk about the difference between displacement and distance later on. So we're finding S, and because we haven't got T, look, we're going to have to use this fourth equation of motion down here. So V squared, that's 0 squared, equals U squared, that's 35 squared, plus 2AS. Now, the 2A part is going to be minus 14, so it's not plus 2AS at all. It's minus 14 and then S on the end. Okay, so the plus in the equation has actually been changed to a negative because our acceleration is negative. Okay, so 35 squared then is 1,225. Okay, I'm trying to find S. When you're changing the subject, you want your subject to be positive, so that needs to go over there. So that's going to be 14S equals 1,225, and then dividing through by 14 gives us 87.5 meters, which is his displacement while he is decelerating. Okay, meaning that if he's closer than 87.5 meters to the lights, he's not going to stop in time. Okay, so he's either going to go through the red light, or he needs to decelerate more by pushing the brakes harder. And number 3 then, so we've got a train, it's already moving at 24 meters per second. So there's our U. It's going to get up to 36 meters per second, so there's our V. The time is 8, so we've got 3 things, and we're going to work out 2 things. We're going to find the acceleration and how far. So this time we're going to find A and S. Okay. To find A, the easiest way of doing that would be V equals U plus AT. So 36 equals 24. Now it should be A times 8, but obviously the rules of algebra tell us that the number's got to go first, so that becomes 8A. Taking away 24 from 36 leaves you with 12 equals 8A. Dividing by 8, you get A is 1.5 meters per second squared. Okay. So that's A sorted, 1.5. And then to find S, okay, I mean, I've got all 4 things. I can pretty much use any equation I want, but let's assume that we did this first, so we didn't have A already. I would have to use S equals a half U plus VT, because it's the only one that doesn't have A in it. So S equals a half of 24 plus 36. And that's all being times by 8. 24 add 36 is 60. Half of 60 is 30. And 30 times 8 is 240 meters. Okay, so that's basic use of the equations of motion, often called the Suvat equations. Just be very, very careful that when you are decelerating, when your initial velocity is higher than your final velocity, A could and should be a negative value. Okay, if you get your numbers back to front, it could come out positive. You will get marked down for that. Okay, so be very, very careful. Right, this one's slightly different, a bit more problem solving here, because there's 2 different runners. You've got lots and lots of values, and the trick here is to match up the right values with the right people, and then decide what you've got, what you need, and what you're missing, and what you need to do first. Okay. So we've got 2 runners, Andy and Jacob, running towards the finishing line of a race. Andy is running at a constant speed of 5 meters per second. Jacob is running at 4.5 meters per second. Andy is 50 meters from the finishing line and is 10 meters ahead of Jacob. Calculate the minimum acceleration that Jacob needs to win the race. Okay, so if we just draw a little sketch of that, so we're all happy with what's going on. Okay, here's our finishing line. Here, dot, 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 dot. Let's make that black and white, like a finishing flag. So we've got Andy in the lead. Okay, and Andy is traveling at a constant speed, and that's a single arrow on a diagram of 5 meters per second. Okay, and he's got 50 meters to go to get to the finishing line. Now he's 10 meters ahead of Jacob, Okay, so we've got a gap of 10 meters there. And he's also, Jacob, running slower, 4.5 meters per second. So if things stay as they are, Andy is not only going to win the race, but the gap between them is going to get bigger because Andy is running faster than Jacob. Okay, first thing to realize here is that Andy is running at a constant speed, which means it's not a SUVAT problem for Andy. Okay, we don't need our equations of motion because he's not accelerating. So that means it's just a speed equals distance over time problem, like you would have done in year 8. So for Andy, his speed is 5. Okay, in this case, speed and velocity aren't too different because they're running in the same direction and nobody's going to turn around. So his speed is 5. The distance that he needs to run, okay, we'll assume this is all in a straight line, so distance and displacement are the same thing, is 50 meters. Okay, what can we work out? Well, we can work out how long it's going to take him to get there. Okay, so the time is distance over speed. 50 divided by 5 is 10. So if Andy continues to run at a constant speed, he will get to the finishing line in 10 seconds. What does that mean for Jacob? Okay, well, it means, well, first of all, Jacob is not running 50 meters. He's running 60 meters because he's 10 meters behind to start with. And this is a SUVAT problem. It is an equations of motion problem because we're finding the minimum acceleration that Jacob needs to win the race. Okay, so he needs to get to the finishing line before Andy in sort of basic terms. So his displacement is 60 meters. He's got 10 seconds to get there, or Andy's going to win the race because Andy will be there in 10 seconds. And really, strictly speaking, he doesn't have 10 seconds because that would be a draw. Okay, so we're going to work on our sort of our boundary edge, and we'll just call it 10. And what we can do at the end is we can fix that with a little inequality when we are done. Okay, his initial speed is 4.5. And what we need to work out is his acceleration. Okay, so we need an equation that links S, U, A, and T. Okay, and that's going to be this one here. Now, lots of people don't like using that equation, especially when they're finding T, because it can throw out a quadratic that needs solving. But we already have T, so this shouldn't be too much of a problem. Okay, so our displacement is 60. We've got 4.5 times 10. That's the UT part of the equation. And I run out of space a little bit and move all these workings over, otherwise I'm going to overlap the sort of the branding on the side there. Plus a half AT squared. Okay, we don't know A, but we know T. T squared is 100, and a half of 100 is 50. So 50A is the AT squared part of the formula. If I expand out that 4.5 lots of 10, that's 45 plus 50A. Take the 45 away, leaves you with 15. It's 50A. Divide by 50, and you get that A is 0.3. Now, what you've calculated there is for the race to finish as a dead heat. Okay, they will get to the finishing line at exactly the same time. You might say that's winning if they're joint first. Okay, so but strictly speaking, that's the minimum acceleration. So we could then give our answer as A has got to be more than or equal to 0.3 meters per second squared. That is the absolute minimum. Any faster than that and he'll win the race by himself, but exactly 0.3 he will win the race, sort of a joint winner with Andy. Okay, so if you've got a question where there's two things going on, you often get cars and buses. Really important you split your page in half. If you need to do a little diagram to get your head around what's going on, do that. Okay, but split your page in half, write down what you know and work from there. And remember, if you haven't got 3 things, you can't use SUVAT. Okay. So now we move on to sort of multi-stage problems where things speed up and slow down, or they travel at a constant velocity and slow down, all sorts of things. And for those, we really do need to start drawing velocity time graphs. Velocity at the side, standard units, meters per second, and time along the bottom, standard units would be seconds. Okay. And I'm very tempted in a lot of these questions, even if it doesn't ask me to, I will draw one anyway. And the benefit of that, if I skip back a few pages, if you think, where do these equations of motion come from? Well, they're all based on area. Okay, so sometimes when you draw your graphs out, you can get bogged down in trying to use equations of motion, and actually you could just be looking at a rectangle, or you could just be looking at a triangle. And you can sit there for 10 minutes working out how to use an equation of motion, and actually you're not meant to be using an equation of motion. You're better off just looking at it as a shape. Okay, so we've got a car starting from rest and accelerating at a rate of 4 meters per second, and that's for 9 seconds. So constant acceleration, remember, is a straight line. Then it travels at a constant velocity for 40 seconds. So that looks like that. And then it applies the brakes for 12 seconds and stops. So it's going to look a bit like that. It doesn't need to be to scale, but what we are going to do is label all of the things that we know. And also what I'm going to do is I'm going to split this into some compound sort of areas. Okay, so I'm looking at this question as 2 triangles and a rectangle. Occasionally you get questions where, unless you look at it as a trapezium, you can't actually answer it. So if you're struggling with your equations of motion, just try using your basic area maths. Okay, so it accelerates at a rate of 4 meters per second squared. Probably the best place to put that is on the slope here, okay, because it is a measure of gradient and it's positive, and that's for 9 seconds. Okay, we're missing a value there. We'll come back and work that out in a second. It travels at a constant velocity for 40 seconds. So that means that across here is 40. But on our scale, and our scale is keeping a total time elapsed, that's going to be 49 seconds. But be careful, you wouldn't use 49 if you're just dealing with a rectangle. And then we've got 12 seconds here for the deceleration. But if you're measuring our total sort of elapsed time, that's going to be 61 seconds, 49 and 12. Okay, and what else do we know? Well, not a lot really. So what I would do, a bit like you were sort of taught back in year 7, maybe year 8, if you're working with compound areas, your best bet is to sort of number them or label them and work with each part individually, and we'll see what we know. So if I start with section 1, and you don't always start with section 1, but I will. U is 0 because we're starting from rest. We know that A is 4, and we know that it accelerated for 9 seconds. That's good news. I got 3 things, okay, and I can work with that in terms of SUVAT. Now, could I work in terms of area here? No, because the only thing I know about the triangle is that the width of that triangle, the base, is 9. I don't know the height. I don't know the area, so trying to use area for that is not going to work. I'm going to have to use some equations of motion. My advice would be work out everything you can. Okay, you might think, oh, we're only interested in velocity or we're only interested in displacement, but while you're there, you never know what you're going to need later on. Work out everything you possibly can. So I'll do V first, and I'm going to use V equals U plus AT. So V equals 0 plus 4 nines, okay, oh, don't need that bracket there, 4 nines, that gives me just 36, whoops, 36. So there you go, that's that value there, 36 meters per second. And we are trying to work out in this question the total displacement. So I'm going to need to know the area as well, okay, and for that, well, I mean, now I know the base and the height. So rather than using an equation of motion, I'm just going to do this. I'm going to say that the area, the displacement, is a half of 9 times 36. Okay, and that's going to come out as 162 meters. Okay, we could have used S equals UT plus a half AT squared because we've got UA and T, but it's a triangle, so don't overcomplicate it. And what I'm also going to do is I'm actually going to write that onto my graph. Okay, because it's all very well having the number underneath, but where we really need it is up on our graph where we can see what's going on. Okay, section 2. Now, initially, all we knew about section 2 was that it was 40 wide, but now we know that it's 36 tall. Okay, I'm not going to overcomplicate it. It's a rectangle. What are we interested in? It's area, because the area under the graph tells us the displacement. So that's just going to be 36 times 40. Okay, it's definitely not an equations of motion problem because it's constant velocity of 36. That's 1,440 meters. Remember, you can pause this meeting at any time. Okay, if you want to have a go to question, if you think I can finish that off from there, just pause it, and when you're ready, press play, and it will resume from wherever you paused it. Okay, you won't miss anything. Okay, on to section 3 now then. What do we know about section 3? Okay, well, we know that its initial for this section is 36. And we know that by the end of it, we stopped. So V is 0. Okay, and we also know from earlier on, it told us in the question that T was 12. So I'm going to work with, I mean, we could just do a triangle. You could do a half of 12 times 36. But I'm going to use an equation this time. So we can do a half of U plus VT. So that's a half of 0 plus 36. It's going to give you the same answer, whatever you do. That's going to be 216 meters. If you add up then our 3 areas, okay, if you add up our 3 areas, you get a total displacement of 1,818 meters there. Okay, and that's the end of that question. And that's a pretty standard velocity time graph question. Okay, working with 3 different areas, having a look at what you know, what you don't know. Okay, next one. A cyclist accelerates from rest for 8 seconds at a rate of 0.8 meters per second squared. He then sees a stopped car and applies his brakes and comes to a rest. If he had a final displacement of 30 meters, calculate his deceleration and the total time he was moving, draw a velocity time graph. Well, I would have done that anyway. Okay, what you'll notice in this question, different to last time, there's no mention of a constant velocity. It says that the cyclist accelerates for 8 seconds. So I'll put that on my graph, and I'll put a little sort of split line down here, so 8 seconds, and I'll put my gradient, my acceleration on there, 0.8 meters per second squared. There's no constant velocity. He immediately applies the brakes and comes to rest again. So this graph actually just comes straight back down again. There is no flat section on the top. Okay. What do we know about this graph? Well, not a lot about the second part, but we do know that the total area, so what I'll do is I'll mark it in here, the total area, and I'll sort of overlap it into both sections so we don't confuse it with just one of those mini triangles, is 30 meters. Okay, and now I'm going to do what I did last time. I'm going to label them. I'm going to write down what I know, and whichever one I know most about, that's where I'll start working. So section number 1, we know that U is 0. Okay, we know that A is 0.8, and we also know that T is 8. Now, what are we interested in? Well, it's probably going to be handy if we know that maximum velocity there, and it's going to be handy, given that we know the total area is 30, if we find the area of just section 1. So I'm going to start with V equals U plus AT again. So that's 0 plus 0.8 lots of 8, which is 6.4. Okay. So that goes up here, 6.4. Anything you work out, add it to your diagram somewhere. Okay. And then our area of our graph then, I mean, we could use UT plus a half AT squared if you wanted. The UT term would be 0. Or we can just say, well, it's a right angle triangle. The base is 8, the height is 6.4. Okay, so a half of 8 times 6.4 is 25.6 meters. Now remember, that is just for mini triangle 1, 25.6 meters. Okay, well, how does that help us with section 2? Because we don't know a lot about section 2. We know that U is 6.4. We know that V is 0, but that's only 2 things. We don't know the area, we do know the height, we don't know the width of it, so we're a bit stuck as well for using area. Well, this is where you've got to be a little bit clever. They told us in the question that the whole area was 30 meters. We know that the cyclist traveled 25.6 meters while they were accelerating. Take that away from 30, and we also know that the cyclist took 4.4 meters. to stop. Okay, that is very easy to miss. Okay, so if you know the area under the graph, you can take it away from the total to find sort of little mini sub areas. So S is 4.4. Okay, right, find the deceleration. So that's A. Find the total time that they were moving. So that's T. Okay. To find A, we're probably better off using V squared equals U squared plus 2AS. V is 0. We need to sort of divide this down here so it doesn't get too messy. So we've got 0 equals 6.4 squared. We don't know what A is, but we do know S is 4.4. So that's 8.8A. Okay, so 6.4 squared, and then bring it over to the left-hand side is minus 40.96. Now don't panic, because we are decelerating, so I am expecting a negative answer. 8.8A divided through by 8.A gets you minus 4.65, exactly as I expected. A negative, it's a deceleration. So A is minus 4.65. Okay, and I'll give myself a little bit of room now then. If I want to find the time, so I've got VU and S. I don't particularly want to use that A value because that has been rounded or could have been rounded. So I'm going to go back to my original 3 values up here because I know that they are accurate. And I'm going to use S equals a half U plus VT for this. S equals a half U plus VT. So that gives us 4.4 is a half of 0 plus 6.4. all times by the time, which is what we're trying to work out. Okay, 0 plus 6.4 is 6.4. Half of 6.4 is 3.2. So that gives us 3.2t. And if we divide through by 3.2, we get a time of 1.38. And that's been rounded to 3 significant figures. Now the total time the cyclist was moving, so that's 8 plus another 1.38, and this is going to overlap where I've written T. It's a bit of a pain if I can move that. Yes, I can. Okay, and that's going to give us then a total moving time of 9.38 seconds. Okay, so a triangular graph and working backwards with the areas on that one. I mean, I'm just going to try and show you as many different types of question as possible. Okay, now I'm a bit weary of time, so we're going to speed up. We're going to try and do one more, which where we know the total area, and then I'm going to try and do one with a negative as well for you. Okay, remember you can always pause this if you want to have a go yourself. Okay, train leaves the station and accelerates for 16 seconds. So I got V here and T there, meters per second and seconds. Accelerates at a constant rate for 16 seconds. Let's put that on there. So 16 seconds up to there. It continues at its velocity until it approaches the next station, and then decelerates at a rate of 1 meter per second before coming to rest. So our graph probably going to look something like that. So now then, what values have we got? No, I got chop there, and let's chop down there. Okay, we know it reaches a maximum velocity of 24, so we can put that in there. We know that it accelerated for 16 seconds, so we can put that in there. Okay, so section 1, section 2, section 3. We also know that in section 3, the acceleration or deceleration, so minus 1 meter per second squared. And then we've got this extra information here, which I haven't done anything with yet. The 2 stations are 6 kilometers apart. And that tells me then that the total area of all 3 parts is 6,000 meters. Remember, we need to be in SI units. Okay. We don't really know enough about section 2 to do anything there. We don't really know much about section 3 either. We've only got the 24 and the minus 1. So it looks like we're going to have to start with section 1, where we know that U is 0, V is 24, and T is 16. And what do we want to know? Well, we want to know the area, really, because otherwise, what are we going to use this 6,000 for? So we're going to find S. Okay, there's no mention of needing to find the acceleration, so we're just going to find S, and we can do that with a S equals a half U plus VT. Okay, if you plug the numbers in there, you get 192 meters. Okay, try and speed up a little bit because we've done a few of these now. Okay. Section 2. The only thing we know, and it's a constant speed or a constant velocity problem there, but the only thing we know is that the speed is 24, so we can't do anything there. Okay, so let's have a look at section 3. What do we know about section 3? Let's go into orange this time. Okay, we know we're at 24 at the start, and we know the train has to stop because it's getting to a station, and we know it's decelerating at -1. Okay, so we need to find the area of that section now then. So that's going to be this time v squared equals u squared plus 2as, because we don't have t. All right, I don't think we're asking for t either, so t is like no use to us in this question. If you put your numbers in, then you get 24 squared, so 0 that side. A is -1, so 2a is -2, and that's times s. You end up doing -576 divided by 2 minus 2. Okay, and that gives us 288 meters. So that's for section 3. Okay, section 2. We still only know the speed, or do we? Okay, go back up. We know the total area of the graph is 6,000 meters. We know that section 1 is 192, and we know that section 3 is 288. Take it away from 6,000, and we've got the area of the middle section, which is 5,520 meters. Okay, that's 6,000. Take away 192, take away 288. So now we do know two things. We know the distance, and we know the speed. Okay, and we want to work out the time that the train is traveling at the constant velocity. So that's distance divided by speed. So that's 5520 divided by 24, which is 230 seconds. Okay, so the width of this rectangle must be 230 seconds. So for it to have the correct area. Okay, so that's a good example there where you got the total area. You need to be a little bit clever. Otherwise, you get a bit stumped in that middle section if you think you've only got one value. Okay, next one. I think I'll skip that one because this graph doesn't go negative, and I'm a little bit weary of time, but that is a past paper question. What I'll do is I'll do the answers to that one, and I'll upload it into the resources section for you. Okay, and the next one there as well, that's a past paper question. I can't remember where I stole that one from. Okay, but that one doesn't go negative either. But if you want to pause the video and have a go, and I'll put the solution up later. Now, the next question I've got now, this one does go negative, and this one is from the 2018 WJC paper. So this one is a good one to actually have a go at. Okay, so it gives us an idea of what we're going to be asked to do in the exam. Okay, so I'm going to draw the graph for the first section. So we've got a vehicle along a straight horizontal road. It's moving at a constant speed of 15 meters per second. So that means my graph, I'm going to be a little bit quicker here, so I'm not going to fully label it. So we've got 15 meters per second there for 2 minutes, and then it decelerates and comes to rest. That looks like that. And if I put on the values we've got, so we know that this is 15. We know that this is 120 because 2 minutes is 120 seconds. Okay. And it decelerates for 12 seconds. So that's 132 in there. Okay. Find the distance A to B. So A is at the beginning and B is at the end. And I know enough here to just do area. Okay. So section 1 is a rectangle, 15 times 120. Okay. That's 1,800 meters, so that's section 1. Section 2 is a triangle. I know it's 12 wide, I know it's 15 tall. So a half of 12 times 15 is 90. Okay, so the total area of that graph there is at 1,890 meters. So that's a quick, easy 3 marks there. Now then, in the second part, the vehicle then reverses with constant acceleration. Okay, now reversing means it's going backwards. If it's going backwards, it has negative velocity. Okay, so if I draw the graph for just this section, I actually need to have room for some negatives. Okay, so it reverses with a constant acceleration of 2 for 8 seconds. Okay, so that goes something like that. Okay, followed by constant deceleration, so that's slowing down. Okay, so it's actually coming back towards 0. Well, that's a bit of a strange looking graph there. You've got to be careful when you're going backwards. Acceleration takes you further away from 0, and deceleration gets you back closer to 0. Okay, so what do we know? So we know that the gradient of this is -2. Okay, we know that that's for 8 seconds. Okay, so for section 1, u is 0, a is -2, and t is 8. Okay, and then we've got a deceleration this side of 1.6. Okay, now I'm running a bit short on time, so what you would need to do, you need to find v, this value here. Okay, find v, and also find s. Okay, and you can do that just by finding the area of the triangle, because once you've got your v value there, you've got the width, you've got the height of your triangle, you can just do that. Okay, for section 2, well, we know that a is 1.6 already, and I put that in as positive because it's coming back towards 0 from a negative value. You can tell from the graph it's positive. Okay, we'll know already that we'll know u because it's from there, look. Okay, and we know that it's going to come to rest, so v is 0, and you need to find t, and you need to find s for those 2 sections. Okay, now then, what you need to do down here, if we put all this together, I'm going to put the 2 graphs together. So we've got from the first part, we've got our constant velocity slowing down to rest. Okay, we did that one in part A. Then you've got part B where it reverses, and then still reversing but decelerating, goes back to 0. Now we know from part A, if I scroll back up, that this area is 1,890 meters. Okay, and you should have from part B the total area of this little section here, but that is a negative area. Okay, so that's going to be a minus value there, and this is where we need to talk about the difference between displacement and distance. Okay, if I draw up my little thing here, so the vehicle, I know for a fact that this vehicle went 1,890 meters forwards. Okay, and then I know, because the graph's gone negative, that it then came back a little bit there. Okay, so this is A, this is B, and this is C after it reversed. If we want to measure the distance from A to C, that's that distance there. So that's 1,890, take away whatever you've worked out for your little negative triangle here. Okay, and that actually is the displacement, because displacement is the difference between where it started and where it finished. Okay, if the question was asking for the distance that the vehicle has travelled, well, it did travel 1,890 meters forward, and it did travel backwards. So in that case, if we're interested in distance, you would add the 2 together. How many meters has this vehicle actually driven is adding. Displacement, what is the difference between where it started and where it finished? That's taken away. Okay, I'll work through this now, and I'll upload it to the resources section. Okay, I'll just show you the other 2 questions I've got. So I've got a couple. Okay, so this question is a little bit older, but WJC. Okay, this one is about 2 vehicles. Okay, so that's a little bit tricky. We haven't had time to get to that, but I will put my answers into the resources section for you later on. Okay, and then we've got then another one there. Now this is the most recent question I could find. Okay, and it's actually very, very straightforward, which is encouraging, because it looks like the WJC have given up on some of the tough ones and are making them easier. Okay, but I'd like to show you everything just in case. And again, I'll put my answers up to that. So if you go on the e-sgol website later on anytime, there'll be a PDF on there, and it'll have all my workings for all of these questions if you've worked through them. Okay, and I think that's probably a good place to stop. So back to you, Mr. Mackenzie.
Thank you, Mr. Weatherhead. I hope you all found that session really helpful. Next week's session is going to be focusing on pure again, which will be with myself. It's going to be looking at exponentials, the gradient of which and how to differentiate them. And also we'll look at, we'll have a few other topics that we'll look at the same time. Okay, thank you very much. Bye.